Good day, everyone. Welcome to exercise 2A, irrational numbers and surds. Now, the main aim of this exercise is to be able to eventually simplify surds. So that's what we are looking at in terms of our lesson objectives. But before we get to that, we also begin to explore a couple of basic rules around square roots. All right, we'll recap that through a couple of examples, as well as also at the start of the lesson, we will begin to explore where does surds sit under the whole number system itself. Right, so just on a general note, you do know that the number line will definitely provide you positioning of all different numbers. So you have 0 down the middle, you have your positive numbers on the right. Okay, so it goes so on and so forth, and you have your negative numbers on the left in itself. Right, these are also called your integers, positive, negative integers within the number line as well. Right, so the number line actually suggests anything that's got to do with your real numbers. So what I'll say is a real number is something that can fall under the number line itself. So whatever numbers that you see on the number line, these are all called real numbers. So this is the big umbrella of all numbers that we already know, right? From year 7 all the way to what we have with year 10. Right, so under real numbers, we have two categories, and they are rational and also irrational numbers. So we first started off in the younger years, of course, learning our whole numbers. You have 1, 2, 3, I can name as well 5 as well, even maybe down to your year 8 where you have your negative numbers. So you have -1, -2. You can also consider your decimal, so -0.1, all that, right? And also maybe even fractions, so like 7/4, if that's improper, or you have 1/5. Now, all these numbers that you see over here, these are your rational numbers. So let me just write that out in terms of the category. What makes these rational numbers in that sense? It can be expressed as a fraction, right? So let's say, for example, they can be written as, and I'll give you an algebraic term, so P over Q, right? So usually it's something over something in terms of an expression as you express that. However, in terms of the condition as well, you do know that your letter P as well as your Q or your numbers, which is P or Q that might replace P or Q, should belong to an integer, right? So this flipped E just means belong to, and then integers is just this symbol that looks sort of like a Z, right? So this has to be the condition where P and Q needs to be an integer. Also, right, your Q that's at the denominator here, it cannot be a 0. Right, so if you pop that in, anything divided by 0 on the calculator, you would see a domain error in there. So therefore, these conditions, as you ensure that your rational numbers are or can be expressed as a fraction, right? So that's a rule of thumb for rational numbers. Right, so with rational numbers, let's say, for example, you have half, right? Half is a rational number because that can be expressed as a fraction. It can also be expressed as a decimal as well, so 0.5. Okay, so decimals are also part of rational numbers, right? And we can also say that under decimal, so in year 8, you have learned this in terms of whether is it recurring, whether is it terminating, whether is it non-terminating decimal. Now, because 0.5 stops at 5, right? So this means that this is a terminating decimal. All right, and then it just falls under your rational numbers as well. Okay, let's say, for example, we have 1/3, okay? And 1/3, you know that if you pop it on the calculator or if you calculate that out, that will lead to 0.3333, so on and so forth. It just keeps running on and on and on. But you know that the number 3 is being repeated all the time, and it goes on endlessly. So in this case, we will call this a recurring decimal. Okay, and as well as you can see that it is non-terminating as well. So it's also non-terminating decimal. Okay, so with that, you can see that clearly under rational numbers, your decimals do come in place as well as you begin to discover that. Now, as you work with Pythagoras theorem in year 9 in itself, so let's say, for example, if you have a triangle, right, and you know that this has a unit of 1, so this length here has a unit of 1, this length here has a unit of 2 here, right? So in order for you to find out what, and of course it must have a right angle here, in order for you to find out what your diagonal line over here is, right? So you know your formula of c squared equals to a squared plus b squared, or flip it around, a squared plus b squared equals to c squared. Right, where do you get your a, b, c? So therefore with your sides, one will be a, one will be b, and the longer side being c. Okay, so subbing in your numbers in that sense, if you're trying to find out what C is, you will then begin to go subbing in your numbers. So you know that, let's say if this is A and this is B here, this will be C here. So I'll sub in my numbers, C square equals to 1 square plus 2 square. Okay, and then after that, I'll try and simplify that before I do the next step. So 1 plus 4, that will give me 5. Yeah, so 5 on the next line. So c squared equals to 5. And then after that, you do need to find out what c is. So because this is a square, in order to remove the square, we'll then use the square root, right? So c equals to square root of 5. Okay. Now, why do we leave this as a cert? That is because if we were to calculate something else, we will need that exact value. Okay, so in fact, if you're using certs, and why we're actually studying certs, this is just so that we can get as close as possible to the exact sort of answer, right? Rather than writing out what square root of 5 is. If you pop that on the calculator, that's square root of 5, hit enter, and you can see it just keeps running on and on and on and on. Okay, so in that sense, this square root of 5 is a cert, right? So going back to our whiteboard over here, if I just pop that up here, right? So we have another category that's certs, okay? And certs will form under irrational numbers. Okay, so with our certs, an example was square root of 5. Now, what makes a square root a cert? So basically, if you can't have a perfect square, or you can't square root that perfect square that's on the inside to give you a whole number, right? In this case, square root of 5, it just gives you, what was the answer? So 2.23606, da da da. So 2.23606, da da da. You can see that the numbers keeps going on and on and on and on and on and on. There is no certain pattern to that, right? Can you express that as a fraction? No, right? So therefore, that falls under an irrational number. Okay, so basically your certs, square root of 5, you consider that. Square root of 3 as well, if you pop that in on the calculator, you can see that just square root of, clear all, square root of 3, hitting enter. Right, you'll see that this is 1.732050, da da da. Okay, it does not quite make sense with the numbers, and you can see that the numbers keep running off and on. There's no certain pattern as well. So once more, square root of 3 is a cert. Okay, so therefore square root of 3 falls under that. Now, if I were to ask you, what about square root of 4? Okay, we all know square root of 4, and if I can pop it on the calculator to just show you that, square root of 4 equals to a perfect number of 2, right? A perfect whole number, I'd say, right? So if you do have a whole number, this means that this is not a cert, right? This falls under your rational numbers, right? So seeing 2, you have your whole numbers. Whole numbers can be expressed as a fraction, right? So this means that square root of 4 equals 2. This falls under your rational number, so it is not a cert. Okay, so hopefully this has given you a good enough sort of example as to what constitutes as certs. How do you identify that? Right? Okay, so certs are irrational numbers. That's what we understand. Now, moving on, how do we actually read certs? Okay, so we have that same example of square root of 3 there. Okay, so what this means is when you have square root of 3, we will just basically read this as square root of 3. So let's say, for example, if we were to put it in more abstract terms, right? If we have square root or n root, okay, n root of a, right? So this means that in simple English terms, this is just the nth root of a. Okay, so same thing, there is no 2 here. Usually it's standard. You don't put the 2 if it's a square root. So therefore, square, because that's true, all right, root of what is that number? So the number that's on the inside, right? So square root of 3, so therefore, nth root of a. Right, so in that sense, as you start to rearrange things now, I will just give you an example of, let's say, and this will be easier as well, as you try to see what is the relationship between this nth root of a and also like the answer that you get over there. So let's say, for example, we have square root of 4. Right, and we know that square root of 4 just basically means, and I'll just write it out here just for the sake of it, just so that you can see it clearly. So square root of 4, popping it on the calculator, and you already know that 4 is a perfect number, perfect square, right? So that will give you 2. Okay, now how do you undo that? So let's say, for example, you're at square root 4, you've already square rooted that, and you get 2. Right, so how do you undo that? So let's say, for example, if you want to undo that and also find out what is that 4 over there, or like try to get 4 once more, okay, this means that you will take 2 and then you square that. Okay, so squaring that of the 2, that will give you 4. Okay, so therefore, as we try to write a generalized statement for that, we can then express this as nth root of a equals to b. So in that sense, n is 2, a is 4, and b is 2, right? Is equivalent to the statement of, and we can say that b to the power of n. So that answer, right, that answer from the previous, and then you square that from whatever that you did with the root there, right? So b to the power of n. So that means it's the same thing as well over here with our illustration. 2 to the power of 2, right, equals to 8. Okay, so it gives you that number that was inside, or that perfect square that was inside the square root itself from there. Okay, so take note of that, because you are basically in terms of flipping that over, using in the case of square root, that will be a square, okay, that you use, and that is what we call an inverse process, right? So in that sense, for this one, you are actually inversing the process of I would say square root or nth root. So in this case, it's nth root. Okay, so take note of this, because that is really important when you break it down to simplifying your surds. Right, so in this example over here, let's just have a look at in terms of our calculation of different surds and how these all sit on the number line itself. So example 1, which is quite close to question 1 in your exercise 2A, use your calculator to arrange the surds: square root of 8, square root of 10, square root of 2, and cube root of 60, right? Cube, because there is a little 3 here, so this means cube root of 60 in order of size on the number line. Okay, so first up, we will have to pop into our calculators the different values. So we have square root of 8. All right, let's just find out what is that on the calculator. So square root of 8. Enter. We get 2.82, and the number just runs off. So what I'll usually do is just to round it off to 2 decimal places. That will do. So that will be 2.83, right? Because 8 is higher than 5, so therefore rounding up. So 2.83. Okay, equals 2.83. So converting all your roots, your square roots or your cube roots into decimals, and then after that putting that on a number line like what the question is asking. So square root of 10, that will be 3.16. So 3.16 square root of 2, square root of 2, that's 1.41. And cube root of 60, right? So cube root just basically means what is that number times that number, that same number, that times that same number, right? So 3 times that you repeat, all right? So if you cube root that, okay, we do get 3.91. Okay, so in terms of decimals and how this all lines up on a number line, okay, you have your number line here. All of them are positive numbers, so we just only need the positive side of the number line. So it starts off with 0, and you know that your smallest is 1 point something all the way until 3 point something, right? So your scale should be until 4. Okay, so then just locating where they will sit. So 2.83 is in between 2 and 3, right? So this is your halfway mark. There's about 2.5. 2.83 is probably, yeah, somewhere down here. So this can be square root 8. Okay, so just putting a dot there will do. And then after that, labeling what is that. Now, next one, 3.16, right? So it's quite close to 3 in that sense. So putting a dot there. And then after that, just labeling square root of 10. Right, square root of 2 gives us 1.41. So 1.41 would sit just before the halfway mark. So just about here. Square root 2. And lastly, cube root of 60, that is 3.91. So that's closer to 4 in that sense. Okay, so cube root of 60. Right, nice and easy with question 1. Right, in order for us to attempt the next couple of questions for questions 2 and beyond, we will have to understand a couple of key basic rules of square roots, right? So I'll just bring you up here to that summary there. Now, I know it's a bit daunting, right? But we'll just use perfect squares to just illustrate that example over there. So with the first one here, let's say, for example, I have, right, square root of 4 in my brackets, and then after that, I'll square that, okay? If you recall your order of operations, BIDMAS, order of operations will tell you that to solve the one that's on the inside of the brackets, right? Because that's B. So this means that when you have a square root of 4, right, that's a perfect square that you're square rooting, you will get 2 on the inside, right? So inside of the brackets, 2, and then followed by your square. Right, so as you simplify that, you can see that 2 squared just basically means 4. Okay, so it's the same thing in terms of what you have, the perfect square of 4 in there. This is just basically your A, right? So if you were to square a square root, right, and this is inversing the process basically, right, you will get 4, which is A over here. Okay, so the same thing, you can already see that you'll just get A. Okay, so 4 is A in that sense. Now, for the second example, we'll again use perfect squares just so that is easier, and you can see how that relates to these different rules that you can see here. Okay, right. Square root of a square on the inside. Okay, so let's say our a is once more a 4 there. Okay, so let's have 4 square, and then after that we square root that. Okay, so working that out, right? So BIDMAS will tell you that you will have to complete the one that's on the inside. So we always work from the inside all the way to the outside. All right, so 4 square is 16. Okay, and that's a perfect square as well. So you can see that square rooting 16 will just give you 4 once more. Okay, so once more, whether your square is on the inside of your square root or outside, you can see that that just gives you that number that's on the inside of that. So that's your A over there. All right, please take note that this is if A and B are positive numbers, right? When you reach the highest as well, you begin to understand as well that this is not quite true, right, when we get to negative numbers, right? You begin to explore that. That will be for another lesson. Right, in the next one, we have the square root of A times square root of B. So we can just sum this up as, let's say, for example, we have square root of 3 times square root of 7. So in that sense, my A is just like my 3. My 7 is just like my B here. Okay, you can simplify them by just popping them together under the square root itself. Operation that's in between should be your multiplication operation. So 3 times 7 square root, okay, that, and then after that equals to square root of 21, right? So it will be the same, okay, in terms of that. If you pop that in on your calculator, if you wish to separate that, so square root of 3 times square root of square root of 3, right? So times square root of 7 equals, right, 4.58 da da da. So we'll just remember 4.58. Whereas if you were to take the square root of 21, this should be the same as well. So, right, so square root of 21. Yeah, that also leads us to 4.58 as well, right? So yes, you can see over here, having these couple of rules will be really good and nifty as well. So square root of A times square root of B will give you AB square root, okay? So just timesing your numbers in between. Now, if you have square root of A, so let's say square root of 35 divided by square root of 7, okay? So we can, once more as well, put them under that same square root, okay? And then 35 over 7, okay? So 35 divided by 7, within that, okay, that will give you square root of 5. Okay, but in that sense, if you were to compare these couple of equations here, you can see if you are multiplying or dividing square roots, right, you will be able to pop them under that same square root there. Okay, so just bear that in mind as we begin to practice a couple of sums in terms of simplifying our thirds. Now let's try a couple of questions together as we simplify surds. Okay, in your exercise for today, you'll be able to complete questions 1 all the way to 6. I'll do just a couple of examples for each of them. Okay, question 2. To F, we have the square root of 108. We can sort of factorize it in terms of factorizing our perfect square. So square root, so 108, right, can also be rewritten as a 36 times 3. Okay, if you pop that on the calculator, it should give you 108 there, right? So what you're doing is actually drawing out that perfect square. So 36 is a perfect square, right? What are perfect squares? That will be 1 square, that gives you 1, 2 square, that gives you 4, right? So these are all your perfect squares. 3 square gives you 9, 4 square gives you 16, 5 square gives you 25, so on and so forth as you go down the list. Okay, so it'll be good for you to get familiarized with what your perfect squares are. All right, so factorizing out your perfect square, that's 36 times 3. Okay, so you know that under your basic rules of your square roots in itself, okay, you can detach them, okay, that's under the same sort of umbrella, I would say, of that square root, detach them to separate sort of square roots, okay? So on the next step, right, square root of 36 times square root of 3. Okay, this you can see square root of 36 will give you, because when you do 6 square, that will be 36, right? So that will give you 6 times square root of 3. Okay, so as you simplify that on the last stage, make sure you just drop that multiplication sign. So 6 times square root of 3. Okay, so that will be your answer for that. Right, nice and easy. So next example, we'll do 2p. All right, so we have square root of 900. So once more, you're trying to find out what your perfect squares are and factorizing that. So you can always factorize that as 9 times 100. Right, so if you square root that, perfect square 9, that's from 3 to the power of 2, right, 3 square. Perfect square of 100, that's from 10 to the power of 2. Okay, so nice and easy over here. Square root of 9, let's detach that from each other. Square root of 100. Simplifying that, you get 3 times 10. Okay, so square root of 9 gives you 3, square root of 100 gives you 10, and then after that, on the final stage, multiplying that to be 30, right? So not necessarily that your simplified form will be a surd, it can also be a whole number. What you're just basically doing in terms of simplifying it, you're just ensuring that whatever number that's on the inside of your square root at the end is not a perfect square, right? It's the most sort of simplest form that you can see that's on the inside. Right, question 3a. So we have 2 times square root of 75, right? So same thing, simplify as well, trying to pick out what our perfect squares are, right? So what sort of perfect squares can we see in there? Now, in 75 over here, right? So we have 25. Yeah, we can do 25 times 3. So in that sense, what we are doing is 2 square root, okay, 5 square, right? We can draw a 5 square, which is 25, right? Times 3. Okay, this will do multiply up to 75. So always double check to make sure that it's still the same. Right, on the next step, we can detach that. So 2 times square root of 5 square times square root of 3. Okay, so we know that from the basic rules of your square roots, you can sort of detach your different factors that you factorize out. Also, you do know that if it's square root of a square here, your answer will just be just the a on the next step as well. Okay, so if you can pop that into a calculator as well, and also if you do know that that rule in itself, it is quite quick as well when you calculate that. So square root of 5 square will just give you 5, okay, times square root of 3. Okay, on the last step, simplifying that, so 2 times 5, giving you 10, and then square root of 3. Okay, so that'll be your final answer. Question 4. Express each as the square root of a whole number. So instead of being able to have the whole number on the outside, we are now popping the whole number on the inside. Okay, so this allows us to recall our knowledge on the reverse process of that. So as we set up our expression over there, so 3 square root of 5, right? 3 times square root of 5 there. Right, so if we are placing our numbers back in the square root itself, don't forget to square that. Okay, so on the next line, this means that square 3 to the power of 2 times 5 square root the entire thing. Right, so if that inverse process, you do know that if you square root 3 squared, this will just give you 3, right? And you're just not changing the value in that sense. Okay, so then expanding that, so your 3 squared will become 9 times 5, okay, square root, and then therefore your answer 54, square root of 54. Okay, so that's what question 4, as you carry that out, as you try to express your entire thing as a square root of a whole number. So square root of that whole number there. Okay, question 5, it says simplify. So question 5 is pretty simple. Let's just give it a go with just one question here. So we have 5a, square root of 2 times square root of 3. Okay, so if you recall your knowledge earlier on your basic square root rules just above over there, you can combine your numbers within that one square root itself. Okay, so on the next line, square rooting that, and then 2 times 3 on the inside. Simplifying that, that will be square root of 6. Okay, so square root of 6 is your answer for 5a. Now, lastly, right, just practicing our knowledge on the last and final of your basic rules of your square root rules, right? So 6a, we have square root of 10 divided by square root of 2, right? So you can combine your numbers within if it's a division. So 10 divided by 2, and then you square root the whole thing. Right, this is not in the simplest form, so we do have to simplify after. So 10 divided by 2 will give you 5 on the inside. Okay, so square root of 5, that will be your answer for 6a. Right, so give it a go with the questions from questions 1 to 6, those that we haven't done together. Please complete all of them. Thank you.